We have today Mike Lewis. He's a research scientist at Facebook AI Research working on natural language processing. So previously, he was a postdoc at the University of Washington and working with Luke Zettelmoyer and on search-based structure prediction. He completed his PhD at the University of Edinburgh and based on combining distributional and logical approaches to semantics. He has a master's degree from the University of Oxford and won the Best Paper Award on EMNLP in 2016. So without further ado, let's get started with today's presentation.
Okay, well, thank you very much for the introduction, Alfredo, and for inviting me to talk. So yeah, this lecture I just wanted to try and give a sort of high-level overview of how deep learning is used for natural language processing these days. So I think it's fair to say there's been really dramatic progress in NLP in the last few years with applying deep learning. So these days, I mean, you can get machine translation systems which will produce translations which blind human narrators prefer to ones produced by professional translators. You can make sort of question answering systems that you ask them a question given Wikipedia and they'll give you answers that are rated as more accurate than the ones that people will give you. And you can have language models that can generate several paragraphs of fluent text. And for all of these things, if you'd asked me maybe 5 years ago, I'd have told you there's absolutely no way any of this is possible in 2020. But there seems to be a few techniques that have been introduced that have really made dramatic differences. One really nice property is actually you can achieve all of these things with fairly generic models. So all the models for all these tasks actually look very similar. There's just a few high-level principles which are really useful. So I'm going to be covering quite a lot of ground on this quite quickly, so please interrupt me often with questions. Right. So yeah, also one thing I should say is that with all the progress we've been seeing in NLP, probably a lot of the stuff I'm going to tell you right now is going to be out of date in a year or two. I mean, I hope we continue to make progress and stuff continues to be out of date. So as well as explaining some of the models we're using, I want to try and sort of give you some intuitions about what kinds of principles are working out well, which will hopefully have a bit more of a shelf life. Okay, so the first topic I want to cover in this lecture is language modeling. Language modeling isn't necessarily a useful task in itself, but it seems to be a really good building block for introducing all the techniques that we'll need later on. I don't know if any of you have seen this before. This is an example from a language model called GPT-2, which came out in 2019. So what's going on here is that we've got some humans supplied some introduction here about scientists finding a herd of unicorns in the Andes that apparently speak English. And then, given that text, they've asked this language model to write some more text that starts with that. And the text we get here is actually quite impressive. Everyone was really shocked that language models could work this well last year. So you can see the continuing text seems actually quite plausible for a news article about this. It's certainly talking about unicorns. The text is very fluent, grammatical. It's not really any flaws there, and it seems to invent quite a lot of details, like the name of the scientist who discovered them. Obviously, all this is complete nonsense. Nothing here is true, but also none of this will look like anything the model was ever trained on. I'm pretty sure this paragraph over his unicorn has no neighbors anywhere on the internet. This is all completely new language, but it's all actually quite high quality text. I'm not going to read all this out, but if you read the rest of the article it wrote, then there are some flaws, but they're quite hard to spot. And generally, this seems to be quite a good language model. So I'm going to try and show you the kind of techniques you need to actually build a language model that works as well. All right. So very briefly, what is a language model? So a language model is just a basically density estimation for text. So we're going to assign a probability to every possible string. And hopefully when our model puts more probability on strings which are fluent English than other strings. So how do we model this density? Well, obviously, there are quite a lot of possible sentences, exponentially many. So we can't just predict classifier students directly. There are different techniques you can do for this, but the one I'm going to talk about is the one that's most popularly used, which is basically to factorize this distribution using the chain rule. So here all we're going to do is this factorization just says we're going to predict the first word, then predict the second word given the first, then the third given the previous two. This is an exact factorization. It doesn't cost us anything to do it like this. So really what we turned is this density estimation problem into a series of classification problems. And these classification problems are of the form, given a bunch of text, predict the next word. And that's going to be a theme through a lot of techniques we have in this talk. So more concretely, we have this, from this example I showed you before, we got this string, the model output, like the scientists name the population after the distinctive horn ovids, and you've got to predict the next word. And the correct word in this case is unicorn. Okay, so at a high level, all these language models look something like this. Basically, we input this text into a neural network somehow. The neural network will map all this context onto a vector. This vector represents the next word. And then we're also going to have some big word embedding matrix. So our word embedding matrix will basically contain a vector for every possible word the model knows how to output. And then all we're going to do is compute the similarity by just doing a dot product between the context vector and each of these word vectors. And we'll get a likelihood of predicting the next word. Then we'll just train this model by maximum likelihood in the obvious way. Okay, so I mean, the detail here is that often we don't deal with words directly. We deal with things called subwords or even characters, but all the modeling techniques remain the same. All right, so all the skill here is in this context encoder. How do we build this? So kind of the first approach people took for this is basically convolutional models. So these convolutional models kind of encode this inductive bias that language kind of has this translation invariance property in that we should interpret a phrase the same way no matter what position it occurs in. So a typical model might look like this, where basically, first of all, for every word, we'll just map it to some vector, which is just a lookup table into an embedding matrix. So the word will get the same vector no matter what context it appears in. And then we'll apply a bunch of layers of 1D convolutions followed by nonlinearities until eventually we end up with some kind of vector representing that context, which really here the vector means what should the next word be. And these models were first, I think this is actually maybe the first language model from Bengio in 2003, or the first neural language model. These kind of convolutional approaches were actually showed to work quite well by Jan Dauphin in 2016 if you apply kind of modern deep learning techniques. These models are very fast, which is great. I should say speed is very important for language modeling because typically we use huge amounts of training data. There's one kind of downside, which is that they're only able to really condition on a certain receptor field. So in this kind of toy example, this word unicorn could only condition on the previous 5 words because of the sort of kernel width and number of layers we're using here. Obviously, like realistic convolutional models have a much bigger receptor field like this, but natural language tends to have extremely long-range dependencies. I mean, for an extreme example, you can imagine if you're like trying to build a language model of a complete book, it might actually help you to be able to condition on the title of the book at all time steps, and obviously the title will be hundreds or thousands of words previously. And it's quite hard to kind of build this into build a convolutional receptor field that's big enough to do this. Okay, so how do we condition our model context? I guess the most popular approach until a couple of years ago was what's called recurrent neural networks. So this is kind of a conceptually quite straightforward idea that basically at every time step we're going to maintain some state, or have some state coming in from the previous time step, which represents what we've read so far. We'll combine the state with the current word we've read, and we'll use that to update our states. And then we'll just iterate this for as many time steps as we need. So on the one hand, I think this seems like quite a natural model of reading. I mean, I think for the most part, people kind of read left to right and maintain some kind of states as they go. At least in principle as well, you can model unbounded context like this. So at least in principle, like say the title of a book would affect the hidden states of the last word of the book. In practice, though, there are some fairly significant issues with this model. Firstly, there's kind of no free lunch here. So by the time the effect of kind of maintaining the state is we're going to compress the whole history of the document reading into a single vector at each time step. And then you can't, once you've read a word, you can never look at it again. You have to memorize that. And that means you have to cram a huge amount of information into a single vector. And this is, firstly, it's a kind of a bottleneck in the model. So, I mean, there's a question about how much information you can really store in one vector, but also it's kind of a practical learning problem too. That's that you get an issue called the vanishing gradient problem, where it means that kind of every time you go through one of these steps, then you'll have some kind of nonlinearity, which will mean that the effective words in the past will kind of get exponentially smaller each time step. And that means that once you have no gradient to a particular word in the past, it's very hard to actually suddenly learn later on that word was important. One final issue I want to mention with RNNs is that they're actually quite slow. The reason for this is particularly for training. So the reason is that in order to build your state for a particular word, you actually have to have built your state for every previous word first. That means essentially you have a big for loop that's going over your entire document. And the longer your document is, the bigger this for loop is. And it means most of these operations you can't actually compute in parallel. You actually have to do it sequentially. And modern GPU hardware is really based around being able to do operations in parallel. Okay. So the convolutional network didn't have this problem. Everything's in parallel, but on the other hand, you get this bounded receptor field. The recurrent models, you have, in principle, an infinite amount of receptor field, but it's quite slow to train. Okay. So the solution to this is now what's called the transformer, which is the model that's used in all the state-of-the-art NLP systems these days. So I'm going to go through transformer in quite a lot more detail than I did with the RNNs or CNNs. Transformers were introduced in 2017 by Ashish Vaswani, and his famous paper called "Attention is All You Need." And they really revolutionized a lot of NLP. So I included a figure here from the original transformer paper. I don't know how confusing this is to you. Certainly when I first saw this figure in 2017, it took me quite a while to get my head around it. And there's quite a lot of details going on in these boxes, so I'm going to just try and slowly drill into them. All right, so what's going on? Basically, you can see we have this input state, this n times this transformer block, and then an output phase. So this n times block thing just means we're going to unroll the same block with different parameters a certain number of times. So this example has 6 layers, which I think they had in the original transformer paper, which seems quite cute these days. These days, people are training models with billions of parameters and many, many dozens of layers. All right. So I'm just going to drill into this block in more detail. So this is kind of the core of the transformer block. You can see it's actually incorporated of 2 different sublayers, which are both very important. Sublayer 2 is maybe the more obvious one. This is just a big feed-forward network. It could be any NLP, but it's important that it's actually quite expressive. And beneath we have this multi-headed attention module. The multi-headed attention is kind of the key building block behind transformers and why they work. So these sublayers are also connected by these boxes labeled add and norm. So the add part just means this is a residual connection, which helps stop the gradients vanishing in large models. The norm here means layer normalization. I'm not going to go into layer norm in detail here, but it's actually very important to make these models work. And there's actually some subtleties about how exactly you do the layer normalization that makes a big difference in practice.
Hey, excuse me, I have a question.
Sure.
So this isn't immediately clear, but could you talk a little bit more about just the intuition behind using multi-headed attention as opposed to a single head? I mean, presumably each head learns something different and attends over its input differently, but what was sort of the intuition behind that?
I'll answer that question a bit. I'm going to go through exactly what multi-headed attention is a bit first, and then I'll try and give some intuitions as to why this is a good thing to do. If I don't answer your question, then please follow me up in a few slides' time.
Thank you.
Any other questions at this stage, by the way?
I have a question. You said that the transformer module uses layer normalization. Why can you provide some intuition into why that works better than group normalization or batch normalization?
I don't think I can actually give a very satisfying technical answer to this. I think a lot of this is quite empirical as to why in NLP layer norm works great, in computer vision batch norm works great. A nice property about layer norm is that it doesn't depend on the batch dimension, which batch norm does. So in practice, that's quite a big advantage because it's quite hard to train with large batches with very large models. Yeah, I mean, you can see people have written lots of papers on actually why things like batch norm even work for computer vision. And I think, at least last time I read, there is still some debate as to actually what it's doing. And maybe the intuitions in the original paper for why even batch norm works are not great. So personally, I would say this is one of the slightly unsatisfying things in deep learning where it works, but it's a little bit unclear why.
Okay, thank you.
Yeah, I might be able to weigh in with a more satisfying answer than that. Okay.
Another question is coming here is, do transformers share weights across time steps like RNN LSTMs?
Yeah, great question. I should have made that clear. Yeah, so all these weights can be shared across time steps. So it's kind of convolutional in that sense. So you have one block and you apply it every time step. You can actually also apply them, use the same weights in every layer, and that works quite well too, though it's not what people normally do.
Thank you.
Any other questions so far?
I think those were the questions I read so far on the chat.
Okay. So what is this mysterious multi-headed attention thing? So here's another figure. I don't know if this helps. So basically, you can compute these three quantities called B, K, and Q here. These stand for query, key, and value, respectively. Do the scale dot product attention operation and then concatenate the outputs. Right. So drilling into this scale dot product attention, eventually we will run out of boxes to expand. It looks something like this. So we're going to compute this query and key, do a dot product and softmax, and use this as a way to sum of the values. Don't worry if that didn't make sense. I will do more detail. So let's take this example where the context here is, let's say, these horns silver white, and we're trying to predict the next word, which in the example before was unicorn. So for the word we're trying to predict, we're going to compute this value called the query. And for all the previous words, we're going to compute a quantity called the key. And these are just going to be linear layers based on the current state of this layer.
Tomorrow we're going to be coding this in practice, so we're going to be seeing this in like all the small details in the code as well.
Great. Okay. So you can think of this query as the model asking a question of its context so far, but it's going to help it predict what the next word should be. So the query could be something like, tell me what the previous adjective is, or tell me what the previous determiner is. And a determiner is a word like these here. And then for the keys, they're going to be things that sort of label the current word with telling you some information about it. So they could be saying, this word is an adjective, this word is a determiner, this word is a verb, something like that. Or it could be something more complex, like it could be like any arbitrary relation, like co-reference or something. So the model is going to compute this question as a query, and then it's going to just do a dot product with all of the keys, and use this to compute, and then you do softmax as well. And this is going to induce a distribution over all the previous words. So here you can imagine a query is something like, tell me what the previous adjective is, and the attention will produce this kind of distribution over these three previous words. It's going to put most of the probability mass on either horned or silver white. We're also going to compute this other value, this other quantity called the value. And we'll do that for all the previous words as well. And maybe the value will tell you something slightly more about what the content of the word is. And then we're going to compute this hidden state by basically marginalizing out the attention distribution. So here, this hidden state is going to be a weighted sum of the values of all the previous words. That's going to be weighted by the probability of that word. So that's basically what's going on the left side of this figure here. I left out this detail about the scaling. That's just a hack to make the gradients more stable. Okay. But there's another detail here, which is that that's kind of single-headed attention I've described so far, but we're actually going to do this thing called multi-headed attention. And that basically just means we're going to compute the same thing with different queries, keys, and values multiple times in parallel. So there's a question before about like what the intuition behind that is. And really it's like you actually want to predict the next word, you need to know lots of different things. So just an example before. Let's see. So let's say the next word here should be unicorns, plural. To know it should be unicorns, I mean, you probably want to know both that it's horned and silver white, because the conjunction of those makes it more likely to be a unicorn. But you also want to know that the determiner here was these and not a. If it was like a horned silver white, it would be unicorn singular. The fact is these means it should be unicorn plural, so you get plural agreements. So you actually need to like look at all of these three words at once to have a good idea what the next word should be. A multi-headed attention is a way of like letting each word look at multiple previous words simultaneously.
A question here is, why are we actually in need of using the softmax?
Why do we use the softmax?
Yeah.
It's a good question. I think, firstly, I mean, having some kind of normalization effect is probably good. I mean, otherwise, when you got to longer sequences, this summation would get kind of bigger and bigger the further you went through. So having a normalization is probably good. The normalization also kind of lets the model discard information too. So it can say that this word just isn't relevant, which is good. I think I have seen people experiment with using things like ReLUs instead, so which kind of give a different way of discarding information, but I think the evidence is the softmaxes work the best.
Another question, sorry, I may have missed this. The mask there in pink, talk about what that is briefly?
Right, sure. So the mask is actually important. So I'm going to say, make a point first. So one of the really big wins about this whole setup of multi-headed attention is that it's extremely parallelizable. So none of this computation of queries, keys, and values at a given time step depends on what you're doing at any of the other time steps. So unlike a recurrent network, you can actually compute all of these simultaneously, which plays very well with the kind of hardware we have these days. So not only are we going to compute all the different heads at once, we're going to compute all the time steps at once in a single forward pass. So that's great, except that if you're computing all the time steps at once, there's nothing to actually stop you words looking at the future. So in this like autoregressive factorization we're dealing with here, then we only want words conditioned on previous words. But as I've described the model so far, the words could look at future words too, which is a problem, because then they can cheat and use themselves on future context to predict themselves. So the solution to that here is so what we call self-attention masking. So a mask is just a upper triangular matrix that sort of has zeros in the lower triangle and like negative infinity in the upper triangle. And we're going to just add this to the attention scores. And the effect of that is going to be that every word to the left has a much higher attention score than every word to the right, so the model will only end up practicing using words to the left. And this is deterministic mask without trainable weights, just values either 0 or negative infinity.
So you'd only mask in case of an application-specific training task, correct? If you had to just build representations, for example, you wouldn't need to mask because it wouldn't matter?
Yeah, that's a great question. So we'll get on to more general representation learning later. So models where you just want a text encoder, you don't need to mask them. Bidirectional context is absolutely helpful. In this case of language modeling, which we're working through so far, then the mask is sort of crucial to make the model mathematically correct and compute the correct factorization. But yeah, great question.
Thanks.
Okay. Okay. So one other detail we need to do to make all this work is add something to the input called the positional embedding. So as I described this model so far, it's actually extremely low bias model. It knows very little about language. The inputs could be anything, and it would work. So in particular, there's like you can model a set or a graph or anything like this. It should be fine. But we know, I mean, in language, there are some properties which are useful. Like, for example, there's an ordering to words, which is really important to how you interpret them. And this model doesn't actually know anything about that. And that's in contrast to the convolutional models and the recurrent models I showed you earlier, which both have different ways of encoding the order of text. So one of the techniques that was introduced in this paper was called positional embedding. There are different ways you can do this. They describe something in the paper which is slightly weird, which I'm not going to describe, but it works just as well to essentially learn a separate embedding for every time step. So for every position in document 0, 1, 2, 3, 4, 5, you just learn a separate embedding, and then you add this to your input. So your input now is a summation of the word vector and some kind of positional vector. And it's very simple, but it gives the model kind of the order information it needs, and it works great. Okay, so why are these models so good? Why does everyone use them? I think the really powerful thing about the model is that it kind of gives you direct connections between every pair of words. So each word can directly access the hidden state of every previous word. And that's a contrast. The convolutional model could maybe get to the state of all the words in this receptor field, but nothing further back in time than that. And a recurrent model, the state has to go through this bottleneck at each time step. So you couldn't actually directly access the previous words beyond the literally one previous word. Anything further in the past than that had to get somehow compressed, and you kind of lost information out of this. Whereas self-attention, you can in principle put 100% attention on any word in the distant past and see exactly what was there. And this just makes it a really powerful model. It avoids things like issues like vanishing gradients quite effectively. And means it can just learn very expressive functions very easily. The other great thing about this is how parallelizable it is. I mean, so on the one hand, this model is doing quite a lot of computation in that it's doing this. So the self-attention operation is quadratic, basically, because every word can look at every other word. And that sounds quite slow. But the really nice thing is you can do it in parallel. So because all these operations are independent to each other, you just do it as one big matrix multiplication. So even though in some sense you probably do kind of more add multiply operations than you would do with the equivalent RNN, you can do all these operations much faster because you do them all at once rather than sequentially. So this is a really good trade-off. I also want to quickly talk about some other things. So I described the stuff like multi-headed attention and positional embeddings and stuff got all the attention when Transformers were first released. But Transformers also came along with a whole bag of other tricks as well. And these tricks were all actually really important to make this stuff work. And in some sense, this paper really kind of modernized NLP, I think. So for example, I mentioned a bit about this use of layer normalization before. The layer norm is really helpful. They also started doing these things like these learning rate schedules. So for whatever reason, to make transformers work well, you have to sort of linearly warm up your learning rate from 0 to your goal learning rate over several thousand steps. And people do warm up learning rates in other settings, but transformers really, really need this to work. Also, things like the initialization actually really do matter with these, and some initializations don't work. And they throw in these other tricks like label smoothing at the output, which again wasn't invented in this paper, but turns out to be quite helpful for the tasks like machine translation. Right. So to give you some idea of how well these things are working, these models I described so far, here are some results on a language modeling benchmark. So the number on the right is what's called complexity, which is a measure of the likelihood of held out data. And here lower is better. So let's see. You see that an LCM for 2016 gets complexity of about 48. You see that Jan Dauphin's convolutional models from 2016 are doing quite a bit better at about 37. Also, people played around with a whole bunch of RNN variants, like there used to be dozens of papers on how you make variations on LSTMs, and some of these are getting low 30s as well. But then when you introduce transformers, you get a really big jump down to go to about 18 and 20. And in terms of language modeling, that's a really enormous jump in performance. I should say these gains we saw were particularly large on kind of long context language modeling. So language modeling so there's some benchmarks where you just get a single sentence to predict. On this task, you actually get a whole Wikipedia article, so potentially thousands of words. And the transformers really shine on this, where you've got thousands of words context to model, and you need to sort of retain information across all of them. Okay. What else did I say? Yeah, so it's a quick comparison just to visualize how transformers and LSTMs look, which kind of indicates some of the points I've shown before. So in the LSTM, you have a lot fewer connections between the words, like everything's kind of very sequential left to right. In Transformer, you don't have any of this. So every word is directly connected to every other word. I guess you should say as well, in some sense, this is maybe a slightly unnatural model for reading. So it kind of suggests that how this model's reading text, and every time it reads a word, it goes and rereads every other word very quickly. But it's very effective. Okay. One other good thing about transformers is that they do scale up extremely well. So with tasks like language modeling, you get essentially infinite amounts of data because I mean, it's just hundreds of billions of words out there. It's far more than you'd ever need. And that means to actually fit this kind of distribution, you need very big models. And if you just keep on adding parameters to transformers, they keep on just working better and better. The examples I showed you before were from this GPT-2 model with 2 billion parameters, which was quite big for 2019, but apparently 2020 we're up to 17 billion, and there are rumors that 100 billion parameter models will be coming along soon.
Excuse me, I have a question. You said transformers are really good for scaling up. I was just wondering, in a language modeling task, if we have like, say a 10,000, 20,000 word document, in an RNN, we can just insert a word step by step, and we wouldn't need a lot of memory per se. Like for a transformer, we need to have a batch size of 10,000, wouldn't we? Like the length of the sequence. But if we have a really long sequence, can we model these long-term dependencies?
Yeah, that's a really great question. I actually meant to mention this point. So, two things I want to say. So firstly, you're absolutely right. The self-attention is, because it's quadratic, the expense obviously grows super linearly, and that is a problem in practice. It means, so mostly transformers do 512 token context windows, which is fairly affordable on GPUs. A lot of these language models will do more than that. They'll maybe model a few thousand tokens, which kind of limits what we can do. But it's definitely the case that a vanilla transformer can't model, say, a 50,000 word book at all. There's a whole sort of cottage industry recently of building variants of transformers, which can do longer sequences. It's a very hot topic right now. There's a bunch of things you can do, but one kind of thing you can do is, like, if you replace self-attention with something like nearest neighbor search, you can do the self-attention sub-quadratic time, and that makes it faster. There are also versions that try to do kind of sparse attention, where like you can't attend to every previous word directly, but you kind of have some dilated set of previous words you can look at, and you don't quite get direct connections to every word, but you can sort of guarantee that you have short paths across every word. There are also things like compressed transformers, which try to bottleneck it all into sort of compress the distant paths into shorter representations. Okay, so you brought up the question of RNN. So at inference time, absolutely, an RNN can model infinite context with absolutely no additional cost, which is great. I mean, it can output like 1 million words and output 1 million verse just fine. Well, the question is actually, is it using this context? And the answer probably is not. So at training time, you can't do this. At training time, you actually have to backpropagate through what's called backpropagation through time, where the LSTM would have to, if modeled in long context, like gradient will have to propagate all the way back through the sort of all the recurrent steps to make a difference to the distant paths. So in practice, firstly, the gradient will vanish like well before you hit 1,000 steps, and also this is very expensive. So this at training time, this isn't for free, and this backpropagation operation will get more and more expensive the longer sequences you're modeling. So that means you can't actually really learn to model distant paths. Even inference time is not expensive, you just won't know what to do with it. And in practice, you probably just forget it anyway, because the you can't remember that much data at once. Right, one more quick point on that, because it's interesting. I guess one case where the RNNs do have an advantage is on certain algorithmic tasks. So if you aren't modeling language, let's say you're doing something like addition or trying to like model parity of a string. So if you use a string of like zeros and ones and ask you are there an even number of ones or not. In those cases, you basically do actually want to apply literally the same operation to every time step. And you don't actually have to have much of a memory, because I mean your state really just needs to be a 0 or a 1. In those cases, the RNNs actually do work very well, because you can train them on short sequences and then they'll show great generalizations of long sequences, all these kinds of toy problems. And I haven't seen anyone try, but I imagine the transformer would actually find it much harder to get that kind of generalization. But that only really applies to these kind of algorithmic problems. In terms of modeling natural language, then, yeah, it seems like various transformers are going to be much more effective than recurrent nets.
Thank you. That was really helpful.
Any other questions on transformers?
I've been addressing the questions I could via text, so I think we are all good right now.
Okay. All right. So next time we want to cover is what's called decoding or inference for language models. So we train this language model. This language model puts hopefully probability maths on things which are good English, and no probability on ungrammatical and nonsensical things. But if you want to like create these samples, like I showed you before, how do we actually generate this text? So often when we think about sort of inference with a graphical model, what we'd like to do is find the max. So like find the sentence which maximizes the language model's probability. Unfortunately, there's as I mentioned before, there's quite a lot of English sentences that are possible, and we can't just like score them all to find the max. Also, these models don't really, there's not many tricks you can do with dynamic programming here. So sometimes you can find the max of over exponential many structures when you have a model that factorizes some way that lets you build a dynamic program, which lets you kind of share state across different hypotheses. But these models don't decompose in a friendly way. So you kind of, whatever choice you make with the first word could affect all the other decisions. All right. So given that, one thing to do is to do greedy decoding. This is where we're just going to take the most likely first word, and then given that word, put it the most likely second word, and then come to guess the most likely third word. And that's okay, but it's, there's no guarantee that it's actually going to be the most likely sequence you want to output, because if you happen to make a bad step at some point, then you got no way of backtracking your search to undo any previous decisions. The slide just says that exhaustive search is impossible. And the kind of hits the middle ground of what's called beam search. So beam search is a way of trying to keep track of an n-best list of hypotheses. And then we're going to just every time step try and keep track, update this list with new words we've added. This may be easier to show you with an example. This slide's from Abigail C. at Stanford. So we start, we output, let's say we have beam size of 2, we'll output these 2 possible words. These are 2 most likely words. Then for each of these words, we're going to generate, work out what our 2 most likely next words are. So obviously if the word is I or he, that does affect what the next word should be, and we'll come up with different hypotheses for each of these. And then every time we're going to kind of compress these down to a list of 2 that we're going to continue processing.
So we are looking for the lowest total sum, is it correct?
Yeah, so these are log likelihoods. So we actually want the highest sum, if that makes sense, which should be where 0 would be a probability 1.
Oh yeah, sure.
So every score is going to be less than 0, but we want to find the sequence with where the sum of the scores is the highest. Did that make sense?
It is. So sorry, yeah, I got the sign flipped. I was meaning like in magnitude, we try to get the smallest number in magnitude.
The smallest in magnitude, sure.
Yeah, sure. Sorry.
Sorry, maybe this is not the best way to show this. Okay.
How deep does the does this like tree go into the beam search? When do you stop looking for like candidate sequences, I guess?
All right, so we basically, one detail I haven't told you is we have this like end of sentence token. And the end of sentence token means once you output that, then this hypothesis is finished. And the aim is to find complete hypotheses, so from the start to the end token, that have the highest possible score. We'll just keep on generating new hypotheses until there's no possible new words we can add that will beat the K complete hypotheses we have still.
Okay, cool.
There is another question here. Why do you think in NMT, very, very large beam size will most often result in empty translations?
Ooh, great question. I have opinions on this. So beam search is good in the sense that it's guaranteed to give you a higher scoring hypothesis than the greedy search I mentioned on the previous slide. But it's kind of a catch here, which is that we're not actually, at training time, we're typically not using a beam. So at training time, we normally just use kind of the autoregressive factorization I showed you before, where like given the sort of n previous correct outputs, predict the n plus first word. what we're not doing is exposing the model to its own mistakes in it at all. So when you do beam search, you can get all kinds of nonsense showing up in your beam for whatever reason, because if you have a very big beam, then probably some of it will be garbage. And in these garbage states, the model has no idea what to do because it was never trained in the situation. So it's kind of unreasonable to expect your model to generalize well, to like making great predictions for some completely nonsensical series of words, which is like very far from its training distribution. And in these cases, the model can do all kinds of weird and undesirable things, like maybe they put a very high probability on something else. For a kind of a classic example of this, I don't know if I don't have one here, but you may have seen these language models get stuck in these feedback loops where they end up just like repeating the same word or phrase infinitely many times. I think this is kind of an example of this, where once the model's like got into this kind of loop, then it doesn't really know what to do, and the easiest thing for it to carry on doing is just keep on looping. So yeah, I think the issue you mentioned with beam search is one of not exposing the model to its own mistakes at training time. So it actually puts a bunch of probability mass and all kinds of things it shouldn't do. Kind of the obvious solution to that is like, well, why don't you have a beam at training time? And the short answer to that is because it's expensive. If you actually got to run this whole inference procedure at training time, that firstly gets rid of all the nice parallelism that we have from the transformer and introduces all the search, and also gives you many more things to score for every training example. So in practice, people tend to just ignore this problem and train a big model for as long as they can, like exploiting like nice fast parallelism you get from this autoregressive version. And then at test time, people will often tune the size of their beam to get the best performance. So in things like translation, like increasing the beam normally helps up to a point, and then makes it worse again when you start uncovering these weird degenerate outputs. But yeah, it's just an unsatisfying thing people have to do. Sorry, that's quite a long answer. Did that answer your question?
I think the student. I will see now what the student says. Like that was a question from a student.
Okay.
And there is another question, a small one on this current slide. Why is the A and 1 in green on the right hand side?
I'm going to admit, I don't know. I saw these slides from Abby. I'm not quite sure what point she was trying to make there.
Okay, never mind. It's okay.
Sorry.
Oh, okay. The point, actually, someone answered because they are interchangeable. Regardless of the one you pick, you get both outputs, pi and tart. Like either you go for A or 1, both of them will tell you pi tart or pi tart.
I'm not sure. So I mean, even if you were to do that, then you can't compress these. It's not like you could get a dynamic program where you can then sort of collapse these hypotheses, because the hidden states for those two hypotheses will still be different depending on which path you took to get there. So I don't know, but okay. Hopefully this illustrates what beam search works.
Sure. Okay.
Okay. Any more questions on this? Okay, this is just a bit more description of how the algorithm looks. Basically, all you do is every time step you generate a distribution of next words for each hypothesis you have, and then you take the top k hypothesis, next words across all your hypotheses, and pull these before you go to the next word. Okay, so All right, so beam search is sometimes the right thing to do, but often it actually isn't. So this is a result of applying beam search to the example I showed you before. So this example from GPT-2 about like scientists finding unicorns in the Andes. You can see here that the model's actually, it starts out putting some good stuff, then gets stuck in this weird feedback loop. So I think, yeah, we're just going to repeat the same phrase over and over and over again. I'll probably just keep on repeating this phrase forever. I mean, I guess kind of what's going on here is like once you said this phrase twice, maybe it's just saying it the third time is actually the most likely thing to do. And then all these other hypotheses get very high transitions get very high probability, even if they're not good. But there's also kind of a slightly different problem, which is like maybe in some cases we don't actually want the most likely sequence after all. Maybe what we want is something interesting. So you see this problem also a lot in like things like dialogue response generation. So you try to build a model to hold a conversation with someone. And if you do this kind of beam search, often what you'll get is it will just give you the most generic response to anything you say. So whatever you say, it'll be like, oh, that's interesting, thanks. And maybe that actually genuinely is the most likely thing to do, because these responses are good in most situations. However, there's not actually a very good experience or a very good system. So how about if instead of taking the max, we're going to sample from the model distribution instead. So this is conceptually kind of appealing, but it doesn't actually give you very good outputs. So this is again the result sampling on that same input. I mean, some of this is kind of good, but then it goes kind of, it gets more weird and degenerate as it goes on. And again, you get this kind of problem where like once you sampled a bad choice, then the model's in state it was never in training. And then once it's not state it was in during training, it's more likely to give you some more bad output, and then you'll get stuck in these horrible feedback loops. Okay. All right, so here's something that actually does work. It's the technique that was used to get you those beautiful outputs we had before. Unfortunately, it's not a very satisfying technique, but it's here for disclosure. So this is called top K sampling. It's introduced by Angela Fan a couple of years ago. Based on top K sampling, what we're going to do is truncate a distribution to just taking the K best and then sample from that. So this is an advantage of giving us kind of diversity, like choosing randomly amongst like good options, but it tries to stop us kind of falling off this kind of manifold of actually good language by when we sample something bad. So the idea is basically just chop off the long tail and just sample from the head of the distribution. And
this is the sampling for the beam search, is it?
Sorry, this isn't beam search. This is just generation. So we're going to, there's not going to be a beam here. There's going to be one hypothesis. I guess you could integrate this beam search too, but this is actually just pure sampling. So we'll generate a word in this method, then use that to generate the next word. Okay. So when you do all that, then this is finally the technique that was used to generate this nice sample. Obviously, this top K sampling is a bit of a hack. It's not very satisfying. I was an author on that paper, so I can be mean about the method, but it does seem to work quite well. I guess one thing to be aware of is like when you see these great samples and things like this, which like OpenAI are very happy to put in their publicity, it's kind of useful to know how it's actually made. And this is not like a real sample from model distribution. The model is like not putting much of its probability mass on this. This is something that's generated by doing a slightly weird inference procedure with the model. I just want to quickly cover, like, all right, so given some text like this, how do we know if it's any good or not? Like, how do you evaluate this? So, like, it's not like evaluating a language model is quite easy. I mean, language modeling is a task of density estimation, so you just look at the log likelihood of how that data. If you want to do instead, like, take some text to model and say if it's any good or not, then this is non-trivial, and it's kind of, people tend to use like these automated metrics like blue and rouge, which measure like n-gram overlap with a reference, but they're not very satisfying. And this is recent research. I'm trying to do automated metrics. Okay. I should probably speed up a bit. All right, so this is that's unconditional language models. So they're generating samples of text. This actually isn't a very useful thing to do. What's much more useful is conditional language models. So models which will, given some input, generate you some output. So, for example, you can think about things like, given a French sentence, like translate it into English, or given a document, generate a summary, or maybe given a dialogue, generate the next response. Or even given a question, output the answer. So these things I call sequence models, because you get given some input sequence, and then you have to generate some output sequence. The first models of these were introduced by Elias Escobar. Look kind of like this with recurrent neural networks, where basically you'd have some encoded network, which would read your inputs, produce some vector, which you can modestly call a thought vector. And then you'd use this to initialize your decoder, which would generate tokens word by word. Again, hopefully you get your theme here that like having these kind of bottlenecks of recurrence is not a good thing to do. You want to have expressive models, which can like see everything. So there's a variation of transformer for sequence models. Here we're going to have two stacks, an encoder stack and decoder stack. Basically, the encoded stack is the same as what I showed you before, apart from the self-attention isn't masked, so every token in the input can look at every other token in the input. The decoder stack will be similar, except that as well as doing self-attention over itself, it's also going to do attention over the complete inputs. So this means that every token in the output has a direct connection to every previous token in the output, and also to every word in the input, which makes these models very expressive and powerful. And when transformers were introduced, they got quite a nice improvement on translation scores over the previous recurrent and convolutional models. So when we train these models, typically what we do is we rely on labeled text. So so it's a trained translation system, for example, you try and get lots of manually translated text. It turns out one of the best ways to get this is things like parliament proceedings, because they always translate the European Parliament will write proceedings in lots of different languages. And then you just use those as inputs and outputs. However, like not all languages are represented in the European Parliament. And these transformers are very data hungry, and like the more text we can throw at them, the better they will do. So there's a question like how we use monolingual text to improve these. So this is actually saying, can we learn without just having input-output pairs? The way we could do this is a technique called back translation, which is quite simple conceptually. First, our goal is to train a translation system that inputs German and will output English. First of all, we're going to actually do the opposite. We're going to train a reverse translation model, which will give an English output German. Then we can run this model over all the English text we can find, and we can find lots of English text on the internet, and we'll translate it all into German. And that gives us like lots more pairs of English and German text. And then we're going to train a forward model that will try and translate this German into English. The nice thing to see here is that it doesn't actually matter how good the initial model is, or it doesn't matter if your reverse model is making mistakes. So if your reverse model makes mistakes, then your final trained data will contain kind of noisy German translated to clean English, which might even help regularize your model, but probably shouldn't hurt its performance when you show it clean German data.
What's a byte text?
Oh, I'm sorry. A byte text just means a parallel text. So the same sentences in two different languages.
Okay, thanks.
Okay. And the nice thing about translation is that the outputs you get are actually always, high quality, because these are the outputs of the system are things sentences you found in the wild on the internet. You're just going to create some noisy inputs that you're going to use for these, pair with these outputs.
Could you go back a slide? The third point, translate billions of words of English to German, is that through the reverse translation model?
Exactly, yeah.
Okay, cool. And you're saying back translation helps generate higher quality translations because of regularization, is that it?
It's not just regularization. It also, the really useful thing is it gives you lots of clean output data. So let's say you want to be a good German to English translation model. You kind of need both to understand German, but also be able to sort of write lots of fluent English as well and understand the English grammar too. And the back translation gives you a way of like incorporating tons of additional English data beyond what you have translations for.
Okay.
So it kind of combines the translation model with the language model. And you can also iterate this procedure too. So you can use that whole setup I described before to train a better model, and then do this to help you generate better back translations, which you can use to train again. And this can be really helpful. I mean, it helps even in English-German, but it's particularly helpful in cases where you don't have much data. So this is on Bernese to English translation, where there isn't a lot of parallel data, but you can get really large improvements by just iterating to back translation. This is from some recent work from FAIR, which I forgot to add a reference for. And again, here are some results on, I think this is English-German, showing some good improvements. One of the direction in machine translation people are exploring now is a massively multilingual MT. So people are trying to not just translate between two languages, but trying to take dozens or 100 languages and try and train a single neural network that can translate between all of these. And if you do this, you start to see big improvements, particularly in languages where you don't have much text. Presumably the model's learning some kind of more general language independent information. Okay, so the last topic I want to cover in this is a really important one, which is self-supervised learning. Right, so Jan must be sick of seeing this cake now, but I think it's actually a good image for this. So the idea is really that to learn stuff, like most of the information we need is going to be, most of the learning we do has to be unsupervised. So we have huge amounts of text without any labels on it. And we just have a little bit of sort of supervised training data. And that's represented by the cake here being the unsupervised learning and the supervised learning just being a little bit of icing on top of the cake. I think actually the recent progress in self-supervised learning for NLP has really proved this metaphor to work. Okay, so I'm going to describe quite a few methods for how you do self-supervised learning for NLP, just so you can try and get some ideas as to what's actually working. So the first one to describe is word-to-back. So the idea of word-to-back was trying to, I think it's really the first paper that showed, got people excited about self-supervised learning in NLP. There had been some previous work from Colbert and Weston, which had also shown some good gains. So the goal here is going to be trying to learn what's called word embedding, so vector space representations for words. And the hope is that just by looking at unlabeled English text, we can learn something about what these words mean. And so the intuition behind all this is that if two words are close together in the text, then they're likely to have some kind of relationship between each other. So the pre-training task we're going to do is going to be a filling in the blanks task. So in this sentence, I'm going to mask out this word in the middle, which is unicorns, and try and predict what this word should be based on the surrounding context. And the hope would be that words like, I don't know, unknown, silver-haired, and horned will somehow are more likely to occur in the context of a unicorn than they are, I don't know, a word like some other animal. So basically, this is going to be a very simple model where basically we're going to take all these context words, we're just going to apply some linear projection to these and map them all down to a fixed size context, and then just do a softmax over our vocabulary. So it looks a little bit like a convolutional language model. The only difference is we're predicting the word in the middle, not the word at the end. And in practice, this model was just a shallow linear projection and was not a very deep model. Okay. So one of the things people find interesting about this was these word embeddings seem to show some kind of surprising structures to them. I'll show you here. It was fun. There's like people debate about how meaningful this is. But basically, the claim was that if you took your embedding for the word king, which you train like this, and you subtract your embedding for the word man, and then you add the embedding for the word woman, you'll get something that's fairly close to the embedding for the word queen. So somehow, just this kind of unsupervised fill in the blanks learning task is inducing this kind of linear structure with kind of meaningful differences between the vectors. Okay, so I mean, this was great. And the really good thing about this was that it's a really, really fast thing to do. So you could train this on billions of words of text even back in 2013. But there's a big limitation, which is these word embeddings are independent of the context. So you get like one vector per word in either vocabulary, but it doesn't know anything about how that word relates to other words. And we know that in language, like a sentence is more than just a bag of words. It depends, each word interacts with other words somehow. And these interactions are, in some ways, a really powerful thing. So in one example, an obvious example is like ambiguous words. So lots of words can have many different meanings. And these word vectors won't capture that, or at best, they'll just be a superposition of all the meanings. Okay. So how do we add context to these? Well, let's see. The most obvious way is to do a language model. I think I'm missing a slide here. Basically, what we're going to do is train a conditional language model. Sorry, an unconditional language model. This is going to be exactly the kind of model I described earlier in the talk. And then, given this language model, the language model will be outputting hidden states every time step, predicting the next word. Instead, when we want to do self-supervised learning, what we're going to do is replace these outputs with some other output that depends on our task. So the pre-training phase is just going to be predict the next word. But then kind of the icing on the cake of supervised learning will be the predicts some other property. So I've shown an example here for a task called path-to-speech tagging, which is trying to say, put some labels on every word here. So it's trying to like label, scientist as a noun and distinctive as an adjective. But you can actually fit all kinds of tasks into this kind of framework. So for example, maybe you could fit something like, this is a sentiment analysis task where you're like given some text and predict like from an Amazon review and predict the rating. So this is a review that says, what can I say about this banana slicer that hasn't already been said about the wheel, penicillin, or the iPhone? And this review got 5 stars. So here we're just going to predict one output from this language model, which is going to be the a token at the end, which is some kind of task-specific label. So one of the really nice things about this approach called GPT was that it kind of eliminated task-specific modeling. So now suddenly we have one model which we can pre-train, and we can then fine-tune this model to do basically any task we want to do that involves classification. So before this, there was actually a few years when like people were building all these crazy architectures. So you build a different architecture to build a question answering model or to do a sentiment analysis model or something. Now you pre-train one big model, and then it's really easy to fine-tune it to do whatever you like. So that was a really big step forward. Unfortunately, that model has kind of the obvious limitation. I said the important thing to do was kind of contextualize words, so like let words know, build word representations that depend on the context. But if you pre-train just a language model, you can only really condition on your left word context. So your representation for each word necessarily can't depend on the representation for any future words. And that kind of limits what the model can do quite a lot. There's one kind of obvious fix to that, which is the approach taken by Elmo. So Elmo, rather than training one left to right language model, also trained a second language model, which operates in the reverse direction. So this is like, starts the last word in the document, and it keeps trying to predict the previous ones. And then you get word representation by concatenating the output layers of your left to right model and your right to left model. So this model is in some ways better in that like now your word representations can condition on left word context and on right word context. And that's really helpful for lots of tasks. But it's still kind of limited in that you don't really model like interactions in these contexts. So these, you just get this shallow kind of concatenation of the left representation, the right representation. And what you really like to do is have kind of like rich interactions between the left context and the right context. Right. And all this brings me to BERT, which is maybe you've heard of, which has made a very big difference in NLP. So BERT actually looks quite a lot like Word2Vec. It's basically a fill in the blanks task. So you take some text, you hide some tokens by masking them out, and then you just try and fill it in the mask. So you get this text like something is a golden something Muppet, and you fill in BERT in yellow. So let's see. Okay, the thing I want you to notice here is firstly, it actually looks quite a lot like Word2Vec. Word2Vec was also given some text, fill in the blanks. The reason it works so much better is that in Word2Vec you would just have this linear projection for like encoding the context words, whereas in BERT you have a very large transformer which can look at much more context and model much more interactions in that context.
So there is a question here. How are contextual representations maintained when fine-tuning for a specific task?
How are they maintained? I guess it's not clear they are maintained. So when you fine-tune for a particular task, you kind of hope the model's learned enough general stuff about language during the pre-training task. And then during the fine-tuning, probably, I guess it's forgetting a lot of this stuff that it doesn't need to solve this particular task. So if you're fine-tuning sentiment analysis or something, it probably can lose a lot of this information during fine-tuning. That seems fine.
Thanks.
Okay. So BERT worked very well. It gave quite large improvements on a bunch of tasks. It was actually achieving the performance of humans, or at least humans approximated by Amazon Mechanical Turk, on a bunch of important question answering benchmarks. But BERT was definitely not the end of the story here. BERT got a lot of people very excited about self-supervised training. Just to quickly summarize details there. So it's a very simple model. Is that you're just going to mask out 15% of the tokens and try and fill in the masks. To build on that, there's some work at Facebook, led by Yin-Han Liu, which looked at scaling up BERT. So
Can
the
I
original BERT formulation actually had a second pre-training objective, which we showed didn't actually help. So we got rid of that.
Can I ask a question for the previous slide? So there were 3 bars. I think I missed one point. The dark blue. What is the dark blue? So we have Amazon Turk.
Oh, thank you. Sorry, I should have said that. Dark blue here is previous state of the art. So
okay, which was
these models were probably Elmo, which is
okay.
So the previous state of the art was definitely using self-supervised training, but improved over Elmo by having this kind of
I see. And glue actually is a benchmark that we've been creating here at NYU.
Exactly, yeah.
Some students were involved.
Yeah, so glue is a big benchmark. It's very important. Okay. So to beat BERT, it turned out all you had to do was firstly simplify its training objective, then just scale it up. So scaling it up here means bigger batch sizes, huge numbers of GPUs, more pre-training text, and then you get very large gains on top of BERT. In fact, much larger gains on top of BERT than BERT had over the previous Elmo work. So yellow here is this new Roberta model. And actually Roberta, the question answering is superhuman by quite a few points, and also on this glue benchmark from NYU, it also outperformed people. And this isn't really about doing anything smart, it's just taking self-supervised training and doing it more. All right.
So why do you say, if you go on this slide here, so there is a very large improvement between BERT and then Roberta in the glue, but not such a huge change maybe in the squad? Or is it just a zooming factor?
Oh, right, yeah.
Maybe it's just a zooming factor, right? Those bars on the left are taller, maybe.
Yeah, I think maybe the scale is distorting this, like you say. I think the point is, if you compare to human performance, I know, BERT was 0.6 points better than people, whereas Roberta is 3.5 points better.
Mm-hmm.
So by that metric, it's actually quite a big jump.
Yeah.
Okay. So I'll just quickly discuss a few of the other things people have been doing self-supervised training. So there's one called XLNet. Basically, so in BERT, when you predict all your mask tokens, you predict all the masks conditionally independently. XLNet has a trick that lets you predict these mass tokens auto-regressively, but in a random order. And they claim some improvements for doing that. It's also span-BERT, which rather than masking out words, you're going to mask out a sequence of consecutive words. There is Electra, which rather than masking words, we're going to substitute words with sort of similar ones, and then have a binary classification problem to tell you which words changed or not. There's Albert, which is BERT, but you tile weights across layers. Also XLM and XLMR, which look into doing this multilingually. It turns out basically you run the BERT pre-training objective, but rather than just feeding in English text, you feed in text in every language you can find. It does a great job learning cross-lingual structure. The key point I want you to take from this is really like, these are all kind of variations on the theme. But in the end, like lots of different things work. The important thing is you have big models, you have bidirectional interactions between the words, and you, if anything, the scale you do this at is the most important thing. So one limitation of these models I described is they're only doing kind of text classification problems, but often we'll want to do problems where the output isn't a classification problem, it's actually output some more text. So pre-training for sequence modeling. 2 papers came out about the same time for this, one of which I was involved in, called BERT and T5. So these models basically are going to pre-train sequence models by denoising text. The pre-training objective looks kind of like BERT. Basically, all you're going to do is take some text, corrupt it somehow by applying some kind of masking scheme, and then rather than predict fill in the blanks, you're going to feed the corrupted text into a seek-to-seek model and try and predict the complete outputs. And this is kind of nice because then you can actually go beyond just masking text. You can apply like any random corruption to the input you want. So for example, you can like shuffle sentences or delete whole phrases or insert new phrases, and the seek-to-seek framework is very flexible. But it turns out just doing simple masking actually works about as well as anything else. And then if you do this, as well as like doing well on things, benchmarks like Squad and Glue, which are classification benchmarks, you can also get state-of-the-art results on tasks like summarization, so where the output is a text. So on the left here, we've got some lengthy document we fed in. We asked the model to produce some kind of summary of this, and it does a great job. It like actually uses context from across the whole document and solves things like co-reference. And generally, as far as you can tell, it seems to show some understanding of the inputs. Okay, we're running out of time a bit. So briefly, I don't think it's the end of the story. Like, I don't think NLP is now solved. A few open questions, which I think are interesting, including how we integrate like background knowledge into this. Do we just want these models to try and memorize the whole internet, or should we build memory mechanisms somehow? As someone brought up earlier, how do we model long documents? We're typically doing 512 tokens here. How can we do, say, a whole book at once? One unsatisfying thing about this is like we have like the same model architecture that can solve all kinds of problems, but it tends not to be able to solve all these problems at once, and typically you fine-tune a separate model for each task. It would be great if we actually have like one model that solves everything. It's kind of related to that, like we basically get human level performance in any task where you have, say, 100,000 labeled examples to do learning from, but Can we build models that do well with like 1,000 or 10 or 1 labeled examples? And finally, but people bring these questions as whether these models are just actually understanding language or they're just really good at breaking at benchmarks. Okay, so to wrap up this lecture, I think the main sort of takeaways from this are these kind of low bias models like transformers work great. We shouldn't try to explicitly model linguistic structure. We should have very expressive models and show them lots of text and let them learn whatever structure they need. Predicting words and text is a great unsupervised learning objective. But if you want to understand language, it's crucial to like incorporate words in context, in particular bidirectional context. Okay, so that's all I have. So thank you very much for listening.
Let's see if we have some questions now. I think there will be several.
Thank you, Mike. Yeah, there's a whole bunch of discussions while you were talking.
Okay.
Links to various papers and explanations of various concepts in the background.
Okay.
Any more questions?
Yeah, I had one. On one of the open questions, it's like understanding whether or not these models are actually understanding the language.
Mm-hmm.
What are some ways that exist right now to quantify and measure that? And how would we do that?
Yeah, okay, so what typically happens is someone says, I know, these models aren't understanding language. If they could, they'd be able to solve this new task that they're introducing. Then they introduce some new task which say BERT can't do, and then say BERT isn't doing it. Then next week someone trains a bigger model and then actually gets human performance on this task. And I think really what's happening is like some people just have intuitions that these neural networks can't be understanding language and they must just be gaming data sets somehow. And to the extent that these models do well, there must be some kind of weird biases in our data sets that the models can exploit without really understanding anything. I mean, it's definitely true that like a lot of our data sets do have biases in them, and like it's kind of hard to make ones that don't do it. It takes a lot of skill. But on the other hand, it's like people are failing to produce good counterexamples to what these models can't do. Like basically, sorry.
Yes, a good example in recent times was the Winograd schema results,
Mm-hmm.
where Winograd schemas are those sentences that are ambiguous, and there is a pronoun that refers to one of the words, and you can tell which word the pronoun refers to unless you know something about how the word works, right? So the standard example is the trophy doesn't fit in the suitcase because it's too large, or the trophy doesn't fit in the suitcase because it's too small. And in one case the trophy refers to the pronoun refers to the trophy, in the other case it refers to the suitcase. And there was a list of those, and people created a data set of those things. And until about 2 years ago, the best results were around 60% for computers. Humans do 95% or something, but the best artificial systems were getting about 60%, and now I think it's about 90%.
Yeah, something like that. Yeah,
something like that, right?
And you don't even get any training data for these. This is just a purely unsupervised problem.
Right. And so the question is, it's clear that those systems have learned something about the role of objects and, a little bit about how the world works by just observing statistics about text. But it's relatively superficial. It's not, as is pretty obvious when you look at text that's generated, we're talking about a unicorn, and then the first sentence is unicorn has 4 horns, right? Which of course doesn't make sense because unicorns have only one. That's kind of the point of being a unicorn. So, the whole idea of, the whole problem of learning common sense has not been solved, very far from it, by those systems, but they work surprisingly well. It's surprising how far you can go with just, looking at text.
Mm-hmm. Yeah, I mean, learning common sense is super hard because in some sense, the things you want to learn are the things that aren't written down. Like no one ever writes down common sense knowledge.
Yeah.
Probably no one ever writes down like a unicorn has exactly one horn and not four. I mean, it just, because everyone knows that. So probably there are limitations to what you can learn from just looking at text.
Right. But can you tell us something about the word, I mean, about some of the work you're doing on sort of grounded language?
Sure, yeah. So, I mean, I put nothing about grounding in this, but there's a whole interesting topic. So I think it's really interesting trying, no one just like produces text to sake of it. People normally use text because it's like somehow a representation of the world. So one topic I was really interested in, like trying to like kind of ground dialogue usage and goals. So rather than trying to build like chit chat systems that talk to each other or talk to people to have a conversation, like can you build systems where you try to achieve some goal? We had some work a couple of years ago on doing this in the context of negotiations. So trying to, there's two of you which are trying to have a conversation to try and come to some agreement with each other. And the only way you can come to agreement is by having a dialogue in natural language, and there's like some outcomes which are good for you, some which are good for them. You have to find some compromise. And then, yeah, I'm kind of interested in the setting because yeah, it seems like actually using language for a purpose is going to be really crucial to really understanding things. Like, I think as going to hence, like there's limits to what we'll learn from just like purely observational use of language, and so just purely seeing text out there in the wild that other people wrote. Like really, to understand things, you want to be agents which are using language to try and achieve some goal and like interacting with people and seeing what works and learning from that kind of signal as well. Maybe that's it's just like the cherry on the icing on the cake or whatever, but I think it is like important that it's there.
You need a cherry. Yeah.
More questions from the audience? Come on, guys. Don't be too shy.
I have a question. The first point on the open questions, how should we integrate world knowledge? So the way I was thinking about is that these billion parameter transformers have so much information about the world in them. And then if we try to fine tune or train this model on some new data, could we like forget some of the earlier concepts that this model had learned? And how would we like quantify what concepts like has the model forgotten apart from the validation set? Does that make sense?
Yeah, so probably you will forget it. I mean, probably if you fine tune this model to do something that doesn't need world knowledge, it will happily forget all the knowledge you told it. I mean, there's some evidence these models are like memorizing quite a lot of facts. So there's a remarkable result recently from this paper, this Google system called T5, which I think has 12 billion parameters. And it's just trained in a self-supervised way. And then you have people, and then you just fine tune to answer questions, which could be questions about anything, but you don't show it Wikipedia or something to like know. You just like see what's memorized, and you can test how much knowledge is in the model from that. And it's not state of the art at that, but it's kind of scarily good. It's like, it turns out if you have 12 billion parameters and you train for a long time, you can just fit huge numbers of facts into these models. I'm not sure it's like the most desirable way necessarily to memorize knowledge, but it seems somewhat effective.
Okay.
That was it.
Thank you everyone for attending. Thank you so much, Mike, for giving a guest lecture. It's good to hear that stuff from the horse's mouth. And we'll see everyone again next week.
Well, actually tomorrow, right? Tomorrow we're going to be implementing everything from scratch. Don't forget.
So tomorrow you get the gory details from the code side of all of this, and then Monday you'll hear about graph neural nets from Xavier Bresson.
Actually, about graph neural net and graph knowledge, is graph knowledge used for language as well somehow? Because I don't know, I have not really knowledgeable about this part of the field.
Well, so you can view, to some extent, you can view all those self-supervised training in text, like Word2Vec, BERT, etc. They use a graph, and the graph is how how often two words appear next to each other or some distance away from each other in the text. That's the graph of similarity between words basically is determined by how far, how often they appear nearby.
Yeah.
And that's when you decide to put them in the input of a neural net because they appear within a sequence. And so you can think of those self-supervised learning systems as basically a very simple form of graph neural net. Well, the graph always has the same structure; it's always linear, and it always indicates your neighbors in a text.
I see.
All right.
All right. Thank you so much, everyone. Have a good evening. Bye-bye.